Okay, so now we're going to talk about logarithmic functions, which are related closely to exponential functions. But before we start, so we can get some really solid background, I want to talk about the concept of one-to-one function. So suppose we do these little balloon sets again like we did when we were talking about functions. And I have as my domain Bob, Bill, Sue, and Dave. And if you have Bob, you end up with a 10. If you have Bill, you end up with a 7. If you have Sue, you end up with a 4. If you have Dave, you also end up with a 10. And you remember that was a function because every x value had one and only one y value. But in some cases, like Dave and Bob, this y value was not unique. Both of them shared 10. And that's the way like parabolas look. So parabola is a function. Well, for a function to be one-to-one, what you want to have happen is you don't want somebody sharing a y value. You want everybody has to have a separate y value. So one-to-one function is every x value has just one unique y value, like this. So if I were going to make a plot, say, and I had a function that did something like this. Let's use a different color here. Well, you can see that when I pick an x value, there's just one y value. So this is x1, this is y1. If I pick another x value here, x2, then y2, just one y value. So this is a one-to-one function. So there's some general function f of x. To juxtapose that with something that's not one-to-one but is a function, again, just think of like an upward-facing parabola. It looks something like this, maybe. So here we have x values. If I had an x value, if I chose an x value here, then I get this y value, but also that y value is associated with this x value. So this is not one-to-one. Okay, one quick and dirty way to do this. Remember when we did functions, we had a vertical line test. So if the function, it's a function if it only crosses the plot once for all x's, and you can see this only crosses the plot once. Same here, it only crosses the plot once as a function. Well, we have to determine if it's one-to-one, you have what you call the horizontal line test. So now in the horizontal line test, if you cross the function only once with a horizontal line, it's one-to-one. But if you look down here, you can see that this horizontal line crosses the function twice, so it's not one-to-one. Quick and dirty little horizontal line test. So why am I talking about one-to-one functions? Well, the reason is we can actually flip one-to-one functions. And what I mean by flip is I can take everything that is over here in the range, and I can put it over here in the domain, and then everything that's over here in the domain I can make in the range, and we have the same connection. So what was it? 4 connected Sue, but now the connection goes in the opposite direction. 4 connects with Sue, 5 connects with Dave, was it 7 was the connection with Bill. So it's an opposite connection, and Bob is 10. All right? So it's still 1 to 1, but now we say that these functions are inverses of each other. So whenever you have a 1 to 1 function, you can flip it and get its inverse. All right? So works for our sets up above, but this also works for point pairs. Suppose you had -3, 27, -2, -8, -1, 1. So these are point pairs. Okay? And they're 1 to 1 because you have one x value gives one y value, and it's different. The y value is different than any other y value here. So, and these x values are all different. So we don't have, so it's a function, it's behaving functionally, and it's behaving 1 to 1. So I can find the inverse of this by simply flipping the x and y terms. So this is 27 minus 3, this is -8 minus 2, and this is 1 minus 1. Okay, so what's good for point pairs is good for whole equations, specifically functions. Say you have y equals 2x plus 3. Well, is that 1 to 1? So in my equation for the line over there, we see that when x is 0, y is 3. I marked it up here already. And down here, when x is -1, y is 1. If you stick -1 in here, you get -2 plus 3, which is 1. Okay, this is our line. Looks something like this. This function is certainly a function, and it is 1 to 1. You can see I could do a horizontal line test, and it would only cross the line at one place. So I should be able to get the inverse of this by just flipping. So I switch out the x and the y term like this. Now if I solve this relationship, I get y equals x over 2 minus 3 over 2. So if this is an inverse of this, then I should be able to just swap these points. So this point here is a point on this plot. 1 minus 1 is a point that is this point. The inverse of that point, the inverse of this point is 3, 0. And if you go to this relationship over here, and you're to stick in values in here, you'll see that if you put in 1, then 1/2 minus 3/2 is -1. That's this point right here. 1 minus 1. So it works. Now one thing that's really interesting is this. This yellow line that I put in here represents another line. It represents the equation y equals x. Anytime you have an inverse, then this line here is like a mirror surface. So the orange line, if you reflect it across this line, it is the exact reflection. The inverse is the reflection across the y equals x line, in other words. So why did I spend 10 minutes going over this stuff? Well, because if we look at our exponential function, say f of x equals a to the x, of course it goes through this point. All the exponential functions go through this point, 0, 1, and then they also end up going through this point, 1, a. And that's just, you can just see that when you, as we talked about before, if you put in 0 in here, this function equals 1. If you put a in here, this equals a. So this is our exponential growth occurring. Well, then, notice that if I were to take a horizontal line here, this is kind of amazing, right? Not amazing, but the exponential function is a one-to-one function. So I can find an inverse for it. So let's just start with these points. So 0, 1 turns into 1, 0, and 1a turns into a 1 here. And again, let's think about this. So this should be a mirror image across here. And a mirror image to this function would look like this. And every point in here is a mirror image across that. So this is the inverse. So f of x, let's call it g of x here. G of x equals f inverse. We indicate that something's an inverse by putting a little -1 in the function here. This is inverse of f of x equals a to the x. So there's a function that is the inverse of the exponential function. Well, so we signify it, y equals the inverse of x, called g of x over here. Y is the inverse of x. What does that equal? Well, we have to make something up. Well, somebody had to make something up. I didn't make it up. And what we call that is log with the same base of x. Same base. Well, why is that the inverse? Why is that the way we'd write that function? Well, think of it this way. If you have y equals f of x equals a to the x, you can rewrite this as a log. Log base a, the same base, of y equals x. It's kind of analogous to saying, like, if we have y equals square root of 2, I can rewrite this as y equals 2 to the 1/2. It's rewriting it in a different way. So I'm taking this a to the x and I'm just rewriting it in a different form. So this is how we relate exponential functions to log functions. Now, since this was 1-to-1, we can get the inverse of this by writing it this way, just switching out the x and the y. And then we can rewrite this in log form. We choose a as the base, log base a. So this is the inverse then. So this is the inverse of this, written in log form.